this, and then we'll use the whiteboard there. All right, so we are given number 33. Okay, we are given an equation y cubed plus y equals to x to the power of 5 minus 4. Okay, and then the question is to find dy dx and the second derivatives, d2y dx2. So in this case, we use the implicit differentiation. And okay, so I will simplify the first derivative notation for the first derivative by y prime and the second derivative by y double prime. Okay, so in this case, if I take the derivative with respect to x from the first variable, y cubed plus y is equals to derivative of x to the power of 5 minus 4 as well. Okay, so you'll see that the easier part is the one in the right hand side, because it only contains x variable. In this case, I have 5x to the power of 4, and then just taking the derivative of y cubed plus y, and the derivative of y cubed is 3y squared, but do not forget to multiply it by y prime. Get y prime there, and then plus y prime once again equals to 5x to the power 4. And in this case, simply y prime equals to just divide 5x to the power 4 divided by this multiplier of y prime here is 3y squared plus 1. All right, so this is y prime. And now we want to look for y double prime. One idea is that just take the derivative of y prime with respect to the variable x, and then using the quotient rule to obtain the result. Another idea is that still we can consider the implicit differentiation from the last two identity here, as to equality here. And in this case, okay, so let us avoid the quotient rule at this moment. So I just take the derivative with respect to x of 3y squared, although we have the product rule, of course, plus y prime equals to the derivative of the last term is 5x to the power 4. So in this case, I should have on the right hand side, I should have 20x to the power 3. And then the derivative of the left hand side here is just we use the product rule. First, let us consider the derivative of 3y squared. The derivative of 3y squared is 6y, and then multiplied by y prime here. And of course, I should multiply it once again by y prime plus 3y squared is fixed, and then the second derivative, y double prime, and obviously the last term is just y double prime. So in this case, if I simplify this, then I have 3y squared plus 1 multiplied by y double prime. On the other hand, the right hand side will becomes 20 x cubed minus, here I have 6y, and then multiplied by y prime to the power 2 there. So in the end, I have y double prime equals to 20 x cubed minus 6y, and then multiplied by y prime square divided by all of this divided by 3y squared plus 1. All right, so that's the first derivative and the second derivative of the y as a function of x. Okay, all right. So I guess that number 30. What is the number 32? Sorry, 32b is oh, sorry, 33b is similar. Okay, and actually it's similar to 32a. Okay, in terms of the first derivative. Okay, so let us skip it, and then we will resume to the case of uh, the to the case of related rates here. So from number 34, 35, 36, 37, 38, and 39, which is consider the 34 and 35, I believe. So now let us choose one of the problem in 36, 37, 38, or 39. All right. Okay. Okay, so let us consider number 36. So in number 36, about the related rates, the problem is as follows. So an iron ball of radius 5 centimeter is covered by a layer of ice. And suppose that the ice melt with the rate 10 centimeter cubic per minute. Okay. How fast does the thickness of the ice layer decrease when the ice is 1 centimeter thick? Okay. And find also how fast the area of the outer layer of the ice decrease. Okay, so uh, let us take a look at the visualization of this problem. Okay, so number 36 here. Let us draw the situation here. So suppose that you have an iron ball. Okay, of course, you may simplify this by take a look at the cross section of the ball. Namely, you consider a circle there to illustrate how the process of this ice melting here. Okay, all right. So in this case, okay. So if I consider okay, the cross section, so that will be a circle. Okay, like this. Okay, and suppose that. Okay, so let us denote it by the blue one as the uh, okay, probably I should. So suppose this is the ball. Okay, so I will denote its radius. Okay, sorry. By the radius is 5, and then covered by snow, and then first I denote the snow by the blue color there. Okay, and then suppose that the layer of the snow there is decrease, is melting. So the volume, of course, is decreasing, and the thing is, we know that the rate of the ice melt with the rate of 10 centimeter cubic per minute. Now the question is how fast the thickness of the ice layer decrease. Okay, so the thickness, let's say, oops, let us consider that the thickness of the ice layer is R there, and suppose that, of course, the ice is melting uniformly. I mean, with the, of course, there is this is the ideal situation, because we the idea is the ice is melting simultaneously at every point, so that it's uniformly melt. Okay, so if we may assume that the thickness is the same, R there, and R decrease uniformly, then the idea is to find the volume. Okay, the volume of the ice here. Okay, so if I just draw this as the ice. Okay, this is the ice. Then we should calculate the volume of the ice, and the volume of the ice is, okay, the volume of ice is, let's say we consider this as a V, then obviously the volume of ice will be the volume of the bigger ball minus the volume of the iron itself, okay, the iron here. And obviously I will have the volume of the ball is 4/3 pi r, the radius of the uh, ice, the radius of iron covered with ice is r plus 5 cube, and the volume of the iron is minus 4/3 pi 5 cube there. Okay, so it's just simply the volume of the iron plus the ice minus the volume of the iron only. Okay, that will be the volume of the bigger ball minus the volume of the smaller ball. All right, is it clear to this point? Okay. Okay, so now let us consider, let us take a look at the equation once again. So the question says that how fast the thickness of the ice layer decrease when the ice is 1 centimeter thick. Okay, okay, of course the radius in centimeter there. Okay, so now let us calculate dv dt, okay, from the formula, and we know that from this information dv dt is 10 centimeter cubic per minute. Okay, so we know from this information that dv dt is minus 10, okay, because it says that the volume decrease. Okay, and now this is the known information. Then we want to find exactly dr dt. I mean the rate of the thickness of the ice layer decrease. So this is known, and the question is what is dr dt? This is the unknown. All right. So from this equation, okay, if I take the derivative, dv dt equals to d dt of the term on the right hand side, namely 4 pi over 3 can be absorbed there, then multiply by the derivative of r plus 5 over 3 minus 5. And you know that the 5 cube there is a constant, so this derivative is 0. And if I take a look at the derivative of this one, just simply 4 pi over 3 multiplied by 3 r plus 5 to the power 2, and then multiplied by the derivative of r plus 5, namely 1. So in the end, this equals to minus 10. Oh, of course, the derivative of r plus 5 with respect to r is 1, and multiplied by the derivative of r with respect to t. So namely dr dt. Okay. So in the end, I can simplify dr dt to becomes, so dr dt equals to, okay, so I on the right hand side is minus 10 over, can simplify this, is a 4 pi r plus 5 square. So 4 pi r plus 5 square. And then the question is how fast the ice layer, the thickness of the ice layer decrease when the thickness is 1 centimeter. Okay, so in the end, just substitute r equals to 1. If I consider r equals to 1, then I will have dr dt when r equals to 1 is minus 10 over 4 pi r plus, 1 plus 5 square. And if I simplify this become minus 5 over 2 pi multiplied by 36, namely minus 5 over 72 pi centimeter per minute. Okay, so that's the answer. Of course, you have to state the answer in terms of the word problem, the solution to the word problem. So the thickness of the ice layer decrease at the rate. Okay, so I will write the conclusion. The thickness of ice layer decreases at rate at the rate. Where is the answer? Minus 5 over 72 pi centimeter per minute. Okay, that's the answer. Okay. Okay, so actually we have the second question. The second question is find also how fast the area of the outer layer of the ice decrease. Okay. So in this case, okay, the area of the outer layer is, okay, let us denote it by A. So A equals to, okay, so it's a function of R equals to 4 pi R plus 5 square, right? Okay. Yeah, so this is just the area of sphere, surface area of sphere of radius R plus 5, because you'll see from the picture the radius of the bigger sphere here is R plus 5. 5 is the radius of the iron ball, and then R is the thickness of the ice layer. Okay, so the surface area of the outer layer is 4 pi multiplied by R plus 5 squared. Okay, so now the question is to ask how fast the area here is, the area here change. And of course, we have to calculate dA dt in this case. So dA dt, okay, just calculate it directly, 4 pi multiplied by 2 R plus 5, and then the derivative of R plus 5 with respect to t is dr dt. Okay, so obviously when R equals to 1, so dA dt equals to, I just calculated 8 pi multiplied by 1 plus 5, and then dr dt. Oh, sorry, I forget to mention that if it's mentioned that it's decrease, then the sign will be a positive. Okay, the negative just to denote that dr dt is decreasing. Okay, all right. Similarly, we have I will continue. So in this case, dr dt is minus 5 over 72 pi. If I eliminate, if I simplify this, so 8 pi 72 pi is 9. This is 6 divided by 3 is minus 10 over 3. Okay, right. Okay. Okay. So the question, the conclusion will be the area of the outer layer of ice decreases at rate, and the rate is 10/3. Do not forget the notation, centimeters square per minute. Okay. All right. Any question up to this point? Any question? Yes. Any question? Is it all right?
Yes, sir, it's clear.
Okay. Yes. Question. Oh. Okay. So just summarize the idea. First, just draw or just sketch the model from the word problem. Okay, so that's the first thing to do. And yeah, we can visualize this actually as the in a two-dimensional setting, just like a circle. Okay, but in reality, this is a ball in 3 dimension, and its inner radius is 5, and the thickness of the ice is R. Suppose that the thickness of the ice is R, so that the radius of the outer layer is 5 plus R, and the volume of the ice is just the volume of the iron and layer of ice minus the volume of the iron itself. Okay, so in this case, it's just the difference between the volume of the ball of radius R plus 5 and 5. Just simply just recall the formula for the volume of the ball with the given radius, and that will be 4 pi over 3 multiplied by R plus 5 to the power 3 minus 4 over 3 pi 5 cube there. Okay, so and we are given the information that the volume decreases at the rate 10 centimeter cubic per minute. So dV dt is minus 10. Okay, please take a look at attention to the minus sign there. Okay, and the question is to ask how fast does the thickness of the ice layer decrease. So in terms of this variable, then we should ask the question, what is dr dt? Okay, we can obtain dr dt from the formula of V. Just take the derivative with respect to t there. So I have dv dt equals to minus 10, but it also equals to the derivative of 4 pi over 3 multiplied by R plus 5 to the power 3 minus 5 to the power 3. So in the end, 5 to the power 3, its derivative is constant. So just take a look at the derivative of R plus 5 to the power 3. And in this case, I have its derivative is 3 R plus 5 square multiplied by dr dt. And if I simplify this, then we obtain dr dt equals to minus 10 over 4 pi R plus 5 square. And then the question is to ask the rate of the thickness of how fast the thickness of the ice layer decrease when R equals to 1. Okay, just substitute R equals to 1 there. Then we can simplify it to the result is minus 5 over 72 pi. And the second question will be, okay, so I first do not forget to write the conclusion in this word. And then the second question is to ask the area of the outer layer of the ice. And of course, we can calculate it directly because the area of the outer layer is just the surface area of the sphere of radius R plus 5. So I will have A equals to 4 pi R plus 5 squared. So in this case, the question is to calculate dA dt. Then dA dt, just take the derivative 4 pi multiplied by 2R plus 5. And do not forget to multiply it by dr dt. Okay. And the last step will be just to insert R equals to 1 there to the formula of dA dt, and also just substitute the formula of dr dt previously obtained to have dA dt equals to minus 10 over 3 after simplification. So the conclusion, do not forget to write it. The area of the outer layer of ice decrease at the rate 10 over 3 centimeters square per minute. Okay. Any question or comment? Right? Question? Okay. Okay, so let us take a look at another problem. Okay. Okay, so let us consider number 38. So number 38, a particle is moving along the graph y equals to square root of x in the first quadrant, so that its distance to the y-axis increase by 3 units per second. Suppose that theta is the angle formed by the positive part of the x-axis and the segment containing the origin and the position of the particle. Then the question is, find d theta dt whenever the distance from the particle to the x-axis is 2 units. All right. Okay, so for number 38, we should draw the sketch of the situation there. Okay, suppose that you have x and y there. Y is equals to square root of x. Oops. Something like this. Then, okay, so suppose that, okay, can consider at a certain instance, yeah, I can draw something like this. Okay, so of course, the coordinate of this is can be written as x comma square root of x. Okay, like this. And theta is this angle. Of course, right. Of course, you'll see that the known information is that it's distant to the y-axis. So the distance at the every point on the curve to the y-axis is just its axis. Yeah, it's x coordinate. Okay? And it's known that it increase by 3 units per second. Okay, so here, okay, the known information is x, and x increase 3 units per second. So it makes sense. So the particle is moving from the origin to the right of the x-axis, okay, along the curve y equals to square root of x. So it's known that dx dt equals to, what is dx dt? Is equals to 3 units per second. Okay, and then okay, theta is the angle. Okay, and of course, if you take a look at this triangle, then what is the relation between x and theta here? And you'll see that if I consider this is O, this is A, this is B, then I know the relation between in this triangle will be tangent theta will be AB, okay, the length of AB divided by the length of OA. Right. So in this case, AB is just square root of x, and OA is x. Right. So I have 1 over square root of x. That's the tangent theta. And the question is to find the theta dt when the distance, okay, be careful with the statement, the distance from the particle to the x-axis is 2 units. Okay, the distance, so that will be, the question is, what is the value of the theta dt when y equals to 2, because of the distance to the x-axis. So y equals to 2, obviously equivalent to square root of x equals 2. So x equals to 4. Okay, so now we can calculate the theta dt by the following, via the following equation. Tangent theta equals to 1 over square root of x. So in this case, okay, we just connect this information. So in this case, if I take the derivative of tangent theta respect to t, and then, okay, the same applies for the derivative of 1 over square root of x. Okay, so in this case, okay, both we use the chain rule in this case. For example, on the left hand side, the derivative of tangent theta with respect to t. Okay, so we know that the derivative of the tangent is secant square. So secant square theta multiplied by the theta dt. Okay, so that's the term on the left hand side. On the right hand side, I will have, so this equals to x to the power minus half actually. So we'll have minus half okay, minus half x to the power minus 3 over 2, okay, because and then multiplied by dx dt. Multiplied by dx dt. Okay. Of course, if I simplify these two terms, then I'll have the theta dt equals to, okay, I will say minus dx dt divided by 2 x to the power 3 over 2, and then secant square of theta. Okay. Of course, secant square of theta is unknown here, so we have to write it in terms of the x variable. Okay, because dx theta is given, x is also obtained there, has been obtained, equals to 4. Then it remains secant theta. Okay, remains to find secant theta. Okay, so of course, if we want to find secant theta, okay, we may use the trigonometric identity relating secant theta and tangent theta, or you may also take a look at the following triangle. Okay, so here x, this is square root of x. Obviously, okay, we can calculate this, and this one equals to x squared plus square root of x squared plus x by using the Pythagorean formula. Okay, so in this case, I can obviously that's so in this case, secant theta will be the ratio of hypotenuse and the side beside the angle theta. So in this case, secant theta equals to 1 over cosine theta. Okay, and this becomes square root of x squared plus x divided by x itself. Okay, and of course we calculate secant square theta. So in the end, d theta dt equals to minus dx dt over 2x to the power 3 over 2. Secant square theta is x squared plus x over x squared. Okay, yeah, actually can simplify this to have the theta dt equals to minus minus dx d theta, and then I have 2x to the power 3 over 2. Okay, so first let us simplify this one. That will be x to the power half. Okay, x to 3 over 2 x squared x half. So that will be 2 okay, x to the power 3 over 2, right? Plus x to the power half. Okay. Okay. So okay, so now when x equals to, okay, what is the information here? X equals to 4, right? We have the theta dt equals to, okay, so what is the x dt? The x dt is 3. So that would be minus 3 over 2, 4 to the power 3 over 2 plus 4 to the power half. Yeah, we simplify this. Okay, so I have 4 square root of 4, 8 plus 2, I believe 8 plus 2 is 10, minus 30, sorry, minus 3 over 20. Okay, that's the result. Okay, any question or comment so far up to this point? And of course, yeah, it makes sense because the value of theta will decrease here, okay, as long as the particle is moving along the y equals to square root of x. Okay, any question? Is it clear? Okay, so once again, the idea for the related, the problem in related traits, first you have to understand what is the known information and the unknown one, okay? And then try to sketch, although not all related traits problem, but usually it's better to sketch it first, and then you know what's going on with the sketch, and then just try to calculate it. Okay, so that's the idea. Okay, so the idea is I draw the curve y equals to square root of x, and the information is the distance from the point on the curve to the x and y coordinate. Okay, and it's known that the rate of change of the distance from the point to the y-axis, namely x, is 3. So the x dt equals to 3. And then since the particle is on the curve y equals to square root of x, so the coordinate of the particle will be always x over x comma square root of x. Okay, and the question is if theta is the angle from the line segment between the origin and the position of the particle with the x positive, yeah, is theta, then we want to find the theta dt. Okay, of course you have to realize how to connect, how to relate the variable x and theta. Okay, and the idea here is we use trigonometry. Okay, the simple trigonometry, and in that case, the simple trigonometry would be the tangent function. So here, if we take a look at the triangle, tangent theta equals to the ratio of the side length in front of the angle, and then the side length beside the angle. So in this case, AB over OA is a tangent theta, and AB, if OA is x, then AB is square root of x. So in the end, I have tangent theta equals to 1 over the square root of x. Okay. So Now we want to find what is the theta dt. The theta dt will be, okay, just take the derivative of tangent theta with respect to t. I will have secant square theta multiplied by, okay, so because that's the derivative of tangent function is a secant square, and then by the chain rule multiply once again by the theta dt. Okay, similarly for the right hand side, should take the derivative with respect to t of 1 over square root of x, and we recall that 1 over square root of x is x to the power minus half, and in the end this derivative is minus half multiplied by x to the power minus 3 over 2, and then multiplied once again by dx dt. Okay. Okay, finally, just write the theta dt in terms of x only, but in this time I have the theta dt is a minus dx dt over 2x to the power 3 over 2 secant square of t. Okay, so now we have to look for the value of secant t in terms of x, and once again you can take a look at the geometric interpretation of this. Is just a triangle, so triangle of the side line x and square root of x, and obviously its hypotenuse is square root of x squared plus x. So in this case, secant t is the inverse, or is just 1 over cosine of t. Okay, just if we take a look at this, get square root of x squared plus x over x. Okay, and then we have to substitute it back to secant theta squared. So we have d theta dt minus dx dt over 2x to the power 3 over 2 multiplied by secant square of t, that value, to obtain, okay, so if I simplify in terms of x, I get this one, and then finally just substitute x equals to 4 there. I have d theta dt equals to minus 3 over 20. Okay. Any question or comment so far up to this point?
Sorry, sir. Could you
Yes,
explain from the sec?
secant theta.
Yes, sir.
Okay, if I take a look at the picture, or I will draw it. So the triangle is, okay, just use triangle is this triangle. This is theta. This is x. This is square root of x. Of course, the hypotenuse will be square root of x squared plus square of square root of x, and the x. Okay, up to this point is understood.
Yes, sir.
And then secant theta equals to 1 over cosine theta. And what is the value of cosine theta? X over square root of x squared plus x, right? X divided by this one. So in the end, I have secant theta equals to square root of x squared plus x over x, right? Is it clear
Yes.
now?
Yes, sir. Thank
Okay,
you, sir.
you're welcome. Any question or comment? Other question or comment? Okay, any question or comment? Okay. So now let us consider about the differential and approximation, linear approximation especially. Okay, so number 40, 41, 42, 43, and as well as 44 and 45. That's for the differential and linear approximation. So let us consider number 40. So number 40 is the question is to find the differential dy for the following function y equals to f of x, where the formula for f of x is given in each part, a, b, c, and d. For example, if I consider 40a, then y equals to x to the power of 4 minus 3x squared plus 1. Okay, then we want to find dy. What is the differential? And simply, okay, so let us recall first what is the differential dy. So if I consider 40, number 40, if I have y equals to f of x, then the differential of y, dy, equals to f prime x dx. Okay, just simply f prime x. So uh, for example, if I consider 40a, y equals to x to the power of 4 minus 3x squared plus 1. Okay, then dy dx, or y prime, is a derivative, equals to 4 x cubed minus 6x. So the differential of y, dy, is just f prime of x, namely this one, multiplied by dx. 4x cubed minus x 6x dx there. Okay. Usually, sometimes we forget to put dx there, but be careful. Make sure that if the question is to write dy, make sure that it's f prime of x dx. Okay, do not forget dx there. Okay, otherwise you just write its derivative only, not the differential of y. Okay, any question or comment? Actually, the same question, the same applies for 40b, c, and d as well. Okay, just simply calculate this derivative and then multiply it by dx. For example, 40b, y equals to cube root of 2x. Just simply write it as 2x to the power 1 over 3. Okay, and then its derivative is 1 over 3, 2x to the power minus 2 over 3. Okay, and then multiplied by the derivative of 2x, namely 2. So I have 2 over 3, 2x to the power minus 2 over 3, and that's the derivative. Of course, is the differential dy is 2 over 3, 2x to the power minus 2 over 3 dx. Do not forget, put dx there. Okay, the same applies for C and D as well. Okay. 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 So number 41. Okay. So we have to know what is the difference between delta y and dy here at a certain point. So in this case, if I consider 41a, okay, if I consider what is 41a, and in this case for 41a here, the question is to okay, we are given a point x equals to 1. So in this case, y equals to x cubed plus 2x, x cubed plus 2x, and here we have x equals to 1. Okay. Okay, x equals to 1, and dx equals to 0.1. Okay. So now the question is to what is the value of delta y and dy. Okay. So the value of delta y there. So delta y, okay, is the difference between the value of the function. Okay, so I will write it in a general form. if y equals to f of x, so delta y is the difference between f evaluated at x plus delta x or dx. Yeah, that's the same. Delta x or dx minus f of x. And in this case, f of x is 1. So if f of x is x cubed plus 2x, then delta y in this case is f evaluated at 1.1 minus f1. So in this case, should be 1.1 cube plus 2 times 1.1 minus when f1 x equals to 1, I have that minus 3, right? Okay, 1 plus 2 minus 3. So that will be the result of delta y. Okay, you may calculate it. 1.1 to the power 3 plus 2 multiplied by 1.1 minus 3. Okay. Okay, so that's delta y. And dy is different. Dy will be the approximation of delta y is, in this case, okay, the general formula is f prime of x dx, or in this case, I can calculate it. Dy is f prime of 1 multiplied by delta x in this case. And delta x is given, namely 0.1. Okay, so that will be f prime 1 multiplied by 0. And recall that f of x is x cubed plus 2x, x cubed plus 2x. So f prime of 1, f prime of x first is 3x squared plus 2. So particular f prime of 1 equals to 5. Just insert or substitute x equals to 1 there. Get f prime of 1 is 5. So the next one, just to calculate dy will be f prime of 1 is 5 multiplied by 0.1, and that will be 0.5. Okay. Of course, you can compare it with delta y. Is is it far or not from 0.5? Okay. Okay, but you may calculate it. So to summarize, delta y is the difference between the value of the function evaluated at x plus delta x and x for given any x and delta x. Dy is just the approximation of delta y, and that is f prime of x dx or f prime of x delta x. And once again, x is given, and in this case, x is at 1, and fx is x cubed plus 2x. So f prime of x is 3x squared plus 2. Simply f prime of 1, just replace x by 1. We get f prime of 1 equals to 5. And dy, once again, is f prime of x dx, and x equals to 1, and delta x equals to 0.1. So in this case, I have 5 multiplied by 0.1, and that will be 0.5. Okay, any question or comment so far up to this point? Okay. Actually, for B and C is the same. The difference is just the formula of the function, okay, and also the value of x and the value of dx as well. And in principle, the general idea is the same. Okay, so delta y is f evaluated at x plus delta x minus fx, and dy is f prime of x dx. Okay, that's it. All right. So okay, so now the idea of differential here can be used to approximation, namely the more precisely linear approximation. And in this case, for example, if I consider 42a, okay, we are given a function, quadratic function, fx equals to x squared minus x. And the question is to find the linear approximation of this function at the point a equals to -1. So x equals to minus. Okay. All right. So actually the linear approximation here is the just looks like the equation of the tangent line at the given point. Okay. So let us take a look at the solution. So once again, for the 2a, right? For the 2a, the function is whether the function f of x equals to x squared minus x, and a equals to -1. Okay? So now, if we want to find the linear approximation, so the idea is to first find its derivative. Okay? Derivative of the function f prime of x is obviously 2x minus 1. Okay? And then just substitute f prime of x equals to a equals to -1. So I have f prime minus 1 equals to 2 multiplied by -1 minus 1. That will be -3. F prime of 1 equals to -3. Okay, so finally, the linear approximation of fx in this case, about a equals to -1 is, okay, so first I write the general formula, and then I will copy its value. Equals to just similar to the equation of the tangent line. Okay, simply fa plus f prime of a multiplied by x minus a. And then finally, just substitute a equals to -1. So I have the linear approximation is L of x equals to, oh, where is the f -1 plus f prime of -1 multiplied by x minus a, x minus -1. That will be x plus. All right, so now just calculate the value of f at -1. So you see that if x equals to -1, I have -1 square. That will be 1 minus -1, and that will be 2, right? The value of, okay, -1 square is 1, minus -1 is 2. And f -1 we just calculated, namely -3 here. So I have -3 multiplied by x plus 1. So in the end, becomes -3x, 2 minus 3 is -1, -3x minus 1. So the linear approximation is just saying that fx is approximated by L of x. Okay, please attention to this symbol. L of x is just approximation of fx. It's not equal to fx. And in that case, L of x equals to -3x. In this case, -3x minus 1. Okay, so that's the linear approximation. Okay, any question or comment so far? Is it clear? Okay, let me know if you have a question or comment. Any question?
Clear, sir.
Okay, is it clear? Yes.
Yeah.
Okay. Okay, so actually okay, so if you consider another part, for example, part B and C, everything is similar. The difference is that just the formula of the function and the given point A here. Okay, so in principle, the formula or the linear approximation of the function f about a certain point A is just given as L of x equals to f of a plus f prime of a, f prime of a multiplied by x minus a. You see that it's exactly the same with the equation of the tangent line at the point a comma f, because the equation of the tangent line at the point a comma f is y equals to fa plus f prime of a multiplied by x minus a. Okay, this actually the linear approximation is just the formula. What is the formula of the tangent line in terms of y as a function of x? Okay. Okay. So if you consider the part B and C, okay, so you'll see that the linear approximation of gx at square root of x plus 3 about a equals to 1 is just simply L of x equals to g at 1, okay, g1 is square root of 1 plus 3 is 4, square root of 4 is 2, g1 plus g prime 1 multiplied by x minus 1. So that will be the answer. The same applies for h of x. The difference, just once again, just only the function. Okay, make sure that you know how to calculate the derivative of the function at the given point, and then once you get the information, just the value of the function at the given point at a plus the derivative of the function at that point multiplied by x minus a. Okay, so that's the basic. Okay. Okay. Okay, so for number 43, 44, okay. Yeah, use differential or linear approximation to estimate the following values. Okay, so you are given for example, let us consider 43a there. So 43a here, the number is square root of 63. Obviously, we can approximate square root of 63. Okay, so what is number 42a, 43a? We want to find the approximation of square root of 63 here, linear approximation one. Okay, so in this case, all right, so we have to define what is the function, okay, and then what is the value of a, basically. Okay, so in this case, the value of the function, start from the function, so let f of x equals to, so from this expression, this is exactly that the function can be square root of x. Okay, and a, this case, equals to 64 there, obviously. Okay, because I can calculate it. I can calculate square root of 64 and then obtain rational number, namely 8 there. Okay, it's in fact it's a positive integer, namely 8. So fa equals to 8. All right, so then the linear approximation of f of x equals to square root of x around or about a equals to 64 is just the general formula is L of x equals to f of a plus f prime of a multiplied by x minus a. Okay, so in this case, a is 64. Okay, so now let us calculate fa and f prime of a, of course. So fa equals to f of 64, and fx is square root of x, so square root of 64, and that will be 8. And in this case, I will have where is the f prime of a. Of course, if f of x equals to square root of x, so f prime of x equals to 1 over 2 square root of x. Okay. So in this case, f prime evaluated at a, or f prime evaluated at 64, just simply 1 over 2 square root of 64. And square root of 64 once again is 8. So I have this one is 1 over 16 there. All right, the result. Now, just write the formula for L of x. Okay. So simply fa plus f prime of a multiplied by x minus a. Fa is 8 plus f prime of a is 1 over 16. X minus a is x minus 64. Okay, right. So if I want to approximate, okay, so if I just put it here, save the space, 8. Okay, so the formula is fa plus f prime of a multiplied by x minus a. So f is 8, f prime of a is 1 over 16 multiplied by x minus a is x minus 64. So if I want to calculate square root of 63, and that will be f of 63, and is approximated by L of 63, and that will be, if I put the formula there, 8 plus 1 over 16 multiplied by 63 minus 64. Okay, 63 minus 64, that will be 1 minus 1, sorry. So I have the result will be 7, 15 over 16, right? Okay. Okay. Okay, any question or comment? Okay. Where is the... Okay, if there is no question, okay, so if I take a look at the Okay, so other problem, for example, for the 3b, here I have uh, the function. We should approximate the cube root of 27.9. So in this case, our function f of x equals to cube root of x there. And first, of course, just find the linear approximation. And obviously, the value of a is 27 there. Okay, just find the linear approximation of cube root of x about a equals to 27. And for after finding the linear approximation there, just substitute x equals to 27.9. Okay, so we get the approximation. Okay, and similarly for 43c there. Okay, so that will be tangent of minus 0.05. So the function is obviously tangent of x about a equals to 0. Then finally, to substitute x equals to minus 0.05. For 43, okay, that will be the function is x to the power 20. Okay, x to the power 20, and then around a equals to 1. Okay, get finding the linear approximation. After finding the linear approximation, just substitute x equals to 0.998. Okay, the same applies for 43e. The function is sine x plus cosine x, and obviously it's about a equals to 0. Okay, and then oh, sorry, be careful with 43. The function will be sine 2x plus cosine x. Okay, because the value of x will be 0.01. Okay, get sine 2x plus cosine of x. The function about a equals to 0. Okay, that will be the answer. Okay, any question or comment so far? Okay, first probably I would like to send the notes first. Where is the note? I think that I haven't saved this. Okay, so I will. Okay, at this moment I should save it first. Okay. Oh, I haven't saved. Okay. I will send the note first. Okay. Okay, now the last probably 15 minutes. So let us take a look at the tutorial problem for chapter 3, part 1. Okay, so this we discuss for the concept review. So for the tutorial chapter 3, part 1, application of the derivative here. Okay, so there are several points here. First, to find the extreme values of the function on the closed and bounded interval. Okay, of course, the candidate for the extreme values on the closed and bounded interval is the endpoint of the interval, the stationary point, and the singular point. Okay, Okay, so you have to know what is the stationary point, the singular point. Obviously, the endpoint of the interval is just clear. The stationary point is the point x for which f prime of x equals to 0. Okay, so the point where the point on the curve where its tangent line is horizontal, or the gradient of the tangent line point is 0. The singular point is the point where the function does not have derivative, or the function fails to be differentiable at that point. Okay. That's a singular point. Okay, so of course, that point are called the critical point. It's just the candidate of the that's just the candidate for extreme point, extreme value. Obviously, if you want to check the whether it's a maximum, minimum, or not, just compare the value of the function at the on the boundary, at the boundary, okay, at the endpoint, and then compare the value of the function at the stationary point, and then compare the value of the function at the singular point. Okay. All right. Now, if we are given, for example, number 1a, this function is a quadratic function, and obviously, the function is always differentiable at any point, so it does not have a singular point. And in this case, also the we are not given the closed and bounded interval, so it's assumed to be for any x. Okay, so we are given f of x for every x squared minus 4x. Then we want to find the the candidate for so the critical point is only a stationary point there. So in this case, I will have, okay, in this case, I will have, okay, so if I want to start with f of x equals to x squared minus 4x, x squared minus 4x. So to find the stationary point, we should find f prime of x first. F prime of x is 2x minus 4. Okay, so the stationary point is the solution to the equation f prime of x equals to 0. So in this case, I have 2x minus 4 equals to 0. So x equals to 2 there. Okay. Okay. So x equals to 2. That's the stationary point. Okay. Right. So the second question is, where is the PDF file? It's missing. Oh, okay. So the second question is we are given the function f of x equals to absolute value of x minus 1, but this function now is restricted only on the interval 0, 2. Okay, and then the question is to ask what is the minimum value of the function. Okay, so obviously where, and then also the type of the function. Okay, so I will summarize it first. P, the function f of x equals to absolute value of x on the interval is 0, 2. Okay, so this function here, actually you can write it as follows. So it's the absolute value of x minus 1. So it's x minus 1 is non-negative when x is greater than or equal to 1. So if x is greater than or equal to 1, then x minus 1 is non-negative. So absolute value of x minus 1 is x minus 1. So of course, Oh, okay. Of course, I have to restrict this only from 1 until 2. And on the other hand, if x is greater than or equal to 0, but less than 1, so you see that if x is less than 1, x minus 1 is negative. So absolute value of x minus 1 becomes 1 minus x. Okay. Okay. So in this case, you'll see that for any point except x equals to 1, this function is differentiable. Of course, if x is greater than 1, the derivative of x minus 1 is 1. If x is less than 1, the derivative of 1 minus x is minus 1. Okay, so there is no problem. However, the problem here, the function is not differentiable at 1. Okay, because, okay, of course, you may draw the graph, or you may check the limit. Limit x tends to 1 of fx minus f1 divided by x minus 1 here is a limit x tends to 1 of fx is x minus 1, f1 is 0. So absolute value of x minus 1 divided by x minus 1. And this one does not exist. Does not exist here. Okay. So the reason, of course, this limit does not exist because if you calculate this right-hand limit, then you get 1. If you calculate the left-hand limit, you get minus 1. So the right-hand limit and the left-hand limit are different. So the limit here does not exist. All right. So that's why the function is not differentiable at 1. So 1 is a singular point of f. Okay. Now, if you want to find the extreme value, then we have to compare. Obviously, this function does not have a stationary point because we know that the derivative of the function other than x equals to 1 is 1 or minus 1. So it's never 0. So it does not have stationary point. So in that case, we will have 3 critical points, namely at the endpoint 0, 2, and 1. So if I calculate f0, 0 is just absolute value of 0 minus 1. So the value of minus 1 is 1. And f2 equals to absolute value 2 minus 1 equals to 1 equals to 1. And f1 is the singular point. Absolute value of 1 minus 1 is absolute value of 0 is 0. So you'll see that the minimum value of f of x equals to absolute value of x minus 1 on the interval 0, 2 is 0. Okay, the smallest one. And the type of the minimum value here is the minimum point here is a singular point. Okay, so x equals to 1 is a singular point. Okay, right. So that would be no problem, I guess. Okay, so let us take a look at the PDF file once again. So number C and D and even E is quite similar. The idea is that we want to use the checking the sign of the derivative means we may conclude the behavior of the function in term the monotonicity of the function. Okay? So recall that if the derivative of the function is positive, then the function itself is increasing. On the other hand, if the derivative of the function is negative, then f is decreasing. Okay. So, for example, if you consider 1c here, if you are given the function, okay, f prime of x, okay, and then you want to know the monotonicity of the function. So, if you are given f prime of x, so this is c. F prime of x is x multiplied by x minus 2. and then you want to know when the function is increasing, when the function is decreasing. Okay, the answer will be to check the sign of f prime on the real line. Of course, you'll see that from this expression, its derivative is 0 when x equals to 0 and x equals to 2. So on the real line, we have 3 parts, minus infinity until 0, 0 until 2, and 2 until infinity. So in this case, the sign of f prime, okay, if x is less than 0, of course, the sign is positive, right? You may take x equals to -1, for instance. And in between 0 and 2, the sign is negative. You may take x equals to 1. Or when 2 until infinity, you may take x equals to 3 to obtain that this is positive. Okay. Okay, before we conclude, before we continue to the conclusion, then you may sketch it. So monotonicity of f, okay, if f prime is positive, then f is increasing. So you may use this graph, increasing, decreasing, and increasing. So the conclusion will be, the conclusion is f is increasing on the interval minus infinity until 0, okay, and on as well as the interval 2, infinity. Okay, all right. Okay. On the other hand, since f prime is negative on the interval 0, 2, then the conclusion will be f is decreasing on the interval 0, 2. Okay, so that would be the result. All right. So of course, in relation to the local maximum and local minimum, you may check if there is a change of monotonicity at around the point 0 and 2. For example, okay, and it also answer the question part E. If in that case, if you consider when now we consider f prime of x equals to 0, so when x equals to 0 or 2, let us consider x equals to 0. Okay, to the left of 0, on minus infinity until 0, we have the function is increasing. Okay, on the other hand, after 0, namely when x is greater than 0 and less than 2, the function is decreasing. So you'll see that in this case, after increasing and then decreasing, obviously f0 is a local maximum value. Okay, increasing and then decreasing, so local maximum value. On the other hand, at 2, if x is in between 0 and 2, you'll see that f of x is decreasing. Okay, and then after x equals 2, x greater than 2, you'll see that the function is increasing. So after decreasing and then increasing, we have a local minimum value. So f2 is a local minimum value. Okay. Okay. So yeah, it also answer question part E. Okay. So the last part here is part D, or you may consider the derivative of part C to C. It's a second derivative is also okay. So okay, but we will use the example in part D. In part D, you are given the second derivative of the function. Okay, and we have to know the relation between the second derivative and concavity right now. And of course, recall that the second derivative is positive, then the function f is concave up. Okay, and of course, the function f If the second derivative is negative, then the function f is concave down. Okay. For example, if I consider part D here, D, I have f double prime of x equals to x squared multiplied by x minus 2. So in this case, we'll have, once again, check the sign of f double prime. And right now, okay, the sign of f double prime here is again 0 and 2, but be careful, we have x squared there. So if x is less than 0, x squared multiplied by x minus 2 is negative. You may take x equals to minus 1, for instance. If x is in between 0 and 2, you'll see that the function here is once again is negative, because x squared is always non-negative. Okay, and if x is in between 2 until infinity, then basically we have positive. So here I will say that since f double prime of x is positive on the interval 2 comma infinity, okay, not including 2, so f is concave up on this interval 2 comma infinity. Okay. Okay. So that's the conclusion. Okay. Of course, we have another conclusion. We know that f double prime of x is negative on minus infinity comma 0 union with 0 comma 2. So the conclusion, so f is concave down on the interval minus infinity comma 2. Okay. And then, okay, so we know where is the location when f is concave up or concave down. And now we want to know what is the inflection point in this case. So recall that the inflection point is the point where the graph of the function change, there is a change of concavity here. Okay, so you'll see that the candidate obviously is 0 and 2. Okay, x equals to 0. So the candidate of the inflection point is 0 comma f0 and 2 comma f2. So you'll see that at x equals to 0, there is no change of concavity, namely it's just a concave down. However, x equals to 2, there is a change of concavity from, so because f is concave up, f is concave down on minus infinity comma 2, and it's a concave up from 2 until infinity, then x 2 comma f2 is a inflection point. Okay, so I will write the conclusion. So if f, so since f concave down on minus infinity comma 2, and its f is concave up on 2 comma infinity, so so there is a change of concavity from concave down till concave up. So 2 comma f2 is the inflection point. Okay, so I guess that's all for today. Yeah, we'll erase the other part. So recall, I have to remind you that we have a quiz at the 4 p.m. in this afternoon. Okay, Do not forget it. The number of the question is the same with the first quiz, namely a 5 multiple choice or short answer question and 1 essay question. Okay, so that will be the uh, uh, information of the quiz. Yeah, of course it's still online. You may access it everywhere at everywhere. Yeah, the material is up to this point, especially I should